In this video, we'll be looking at nuclear chemistry. And the reason why we're spending a chapter dealing with nuclear chemistry is because of the role that nuclear chemistry can play in medicine and healthcare. First thing we want to talk about regarding nuclear chemistry is the idea of radiation. Now, this term gets used a lot, and a lot of times in popular media and the press and in slang, it kind of gets used inappropriately. So we want to make sure we are having a thorough definition of what radiation is. So when we talk about radiation, what we really mean is the spontaneous emission of particles and/or energy from an unstable nucleus. Now, there's a term in this definition that we also have to be a little bit careful of, and that's that spontaneous term. Now, when we use the term spontaneous in everyday language, we often mean immediate or quick, or there's a fast kind of connotation that goes along with that. In science, when we say spontaneous, we don't necessarily mean that that event will happen fast or rapid in the same way we would when we would just be speaking about that term in everyday conversation. In science, spontaneous has a different definition. In science, when we say spontaneous, we mean that the event will eventually occur naturally without any other outside influence. Even when it could happen very, very slowly, though. It could happen fast, but it doesn't necessarily have to happen fast. In science, spontaneous just means that it will happen. It could take quite some time for that event to happen, but it will happen without any other influence involved. And this idea of this unstable nucleus emitting these particles and energy, the driving force behind that is something that happens in all of the events that occur in nature, in the universe. Whenever something is in a higher energy state, it wants to give off that energy in order to get to a lower energy state. For us, in the case of the nucleus, by emitting that radiation, that previously unstable nucleus, it shed off some of its excess energy. And as a result, it's going to become more stable. Now, for the most part, you see here, we're really focused on the nucleus. For virtually any other chemical reaction we're looking at, we're not focused on the nucleus, we'd be focused on the electrons. Nuclear chemistry is the one kind of exception where we're not interested in the electrons. Instead, we're interested in what is occurring in that nucleus. We want to talk about some of the common types of radiation and how we would represent them. And this goes along very similarly to what we talked about for isotopes. So one very common type of radiation is an alpha particle. And what an alpha particle consists of is a helium nucleus. Well, what that really means is an alpha particle is 2 protons and 2 neutrons. 2 protons and 2 neutrons go into making up an alpha particle. Now, there's 2 different ways we can represent this, and it's very similar to the isotopic designation, except we don't really worry about the charge in any way. So if we have 2 protons and 2 neutrons, what would our mass number be? Well, our mass number would be 4 when we think about how we're representing that. And of that 4 mass number, 2 of those are protons. So in the atomic number spot, we would put a 2 there. Now, one way of representing an alpha particle would be to use the Greek letter alpha. So here's one way, kind of highlighted in yellow in the symbols on how to represent that. There's another way we could represent that as well. You could also represent that by saying, oh, the mass number is 4, so I'm doing this in green. Mass number is 4, still 2 protons, so the atomic number is 2. Now, instead of invoking and using the Greek letter, instead we can just kind of fall back to something that is maybe a little bit more similar to what you did with the isotopes. What element consists of 2 protons or has an atomic number of 2? That would be helium. So you'll see alpha particles represented both of these ways. Another form of beta particles, or another form of radiation, are beta particles. And for the description of a beta particle, what a beta particle is a high energy electron. So right away, this sounds a little bit confusing because we said radiation comes from the nucleus. And we know that in the nucleus, we don't have the electrons. We know the electrons reside outside of the nucleus. So how can this be a form of radiation? Well, let me kind of talk you through how that happens. Remember when we did subatomic particles, or those things that go into making up an atom, in the nucleus we had protons and neutrons. And we said that neutrons were just slightly heavier than protons. Well, the amount they're slightly heavier by is about the mass of an electron. So what can happen in the nucleus? So what can happen in the nucleus is, in the nucleus, a neutron can decompose into a proton. A neutron turns into a proton. Kind of the byproduct of that, what can result from that transformation is, in the course of that neutron becoming a proton, a high energy electron is emitted. That would be the kind of spare parts, the waste products in that transformation. That high energy electron that's formed in that transformation from a neutron to a proton, that's that beta particle. So we have 2 different ways of representing that beta particle. It's an electron, it's a high energy electron. Well, we know that in terms of mass, the electron does not have a mass. So our mass number is going to be 0, that I'm highlighting in yellow in the symbol category here. Now, when we think about an electron, we can think about an electron as the exact opposite of a proton. So a proton, we know we'd represent that with atomic number 1. Well, since the electron is the exact opposite of a proton, we could use -1 for that atomic number. And one way of representing that beta particle would involve kind of the Greek letter beta, kind of highlighted in yellow. Another way of representing it, where you don't have to use Greek letters necessarily, would be to say, okay, the mass number is still 0. It's still an electron, which is the opposite of a proton. So highlighting in green here, that -1. Now, instead of using a Greek letter, we can use a lowercase e to kind of represent that, hey, we're dealing with an electron. I'm going to cross off positrons from our list here. You don't run across positrons enough to worry about, so we're not going to worry about memorizing the names or the descriptions or the symbols of how to represent these. We're going to focus on the ones you're much more commonly going to come across. Another form of radiation would be a proton. Well, we know what a proton is. Proton is the nucleus of a hydrogen atom, being a hydrogen atom only has 1 proton. How would we represent that? A couple different ways of representing that. We know that a proton has a mass of 1. Proton also has an atomic number of 1. So we could use a lowercase p for proton. That would be okay. It's a little bit confusing because a lowercase p looks like a capital P, so you might get mixed up with phosphorus or proton. Which one are you dealing with? There's another way of representing it as well. Mass number would still be 1. Proton has a mass of 1. The atomic number would be 1. It is a proton. And here we're just using the element that corresponds with a single proton. 1 proton would be hydrogen. So we have 2 different ways of representing that. Again, you often see both ways used. Another form of radiation can be a neutron. We know what a neutron is. It resides in the nucleus. It's a particle with a mass about the same as a proton, but no charge. How could we represent a neutron? Well, we recognize that a neutron has a mass of 1. It's not a proton, so we would use the atomic number of 0. The only way you'll ever really see a proton represented would be with a lowercase, or the only way you'd see a neutron represented would be with the lowercase n. And there's really no other good way of representing a neutron. Now, the last type of radiation, gamma ray, is a little bit different than the 4 previous ones that we did. Gamma rays are going to be different than alpha particles, beta particles, protons, neutrons. Everything above that red line that we've already talked about, well, that was a particle. A gamma ray is not a particle. A gamma ray is just very high energy electromagnetic radiation. It's not particle in nature. It's just raw energy. And the way we really represent that is with the lowercase Greek letter gamma. What you'll sometimes see, and I'll try to draw this on the side, is what you'll also sometimes see to really get at the fact that this is not a particle. So I'll do this in the upper right-hand corner of the screen. You'll write the symbol for the gamma, that Greek letter, and then for both the mass number and the atomic number, you'll often see that represented with zeros as well, just to really kind of highlight the fact that this is not a particle. This is just energy. So what you want to be able to do is you need to know the 5 common types of radiation: alpha, beta, proton, neutron, gamma. What is it? What is that description? As well as how are those things represented using symbols? Easiest way of dealing with this, again, I think, is to flashcard these. Next thing we want to work on our chapter on nuclear chemistry is we want to be able to complete nuclear equations. So we want to be able to take a nuclear equation that is missing a piece and being able to figure out what that missing piece is. So we'll talk about how to do it on this slide, and then we will do a couple of examples that illustrate this process. And the key thing for completing a nuclear equation is we're going to treat the reaction arrow in that equation in a similar way to what you might do to an equal sign in math. In math, when you have an equal sign, you know that whatever's on the left-hand side of the equal sign and whatever's on the right-hand side of that equal sign may look very, very different. The two sides, the left-hand side and the right-hand side of that equation, may look very, very different, but are numerically equivalent. There's got to be some equivalency. And there's going to be 2 equivalencies we're going to talk about. The first is the idea of an atomic number equivalency. The sum of the atomic numbers on each side of the equation must be equivalent. We're also going to see an equivalency for the mass numbers as well. The sum of the mass numbers on each side of the equation must also be equivalent. So when we're figuring out the missing pieces, we're really figuring out mass numbers and atomic numbers for missing pieces such that each side of this equation will be equivalent. So now that you kind of saw the steps, now we want to do this with a couple of specific examples. So here's an example of completing a nuclear equation. We see this nuclear equation. We see a couple isotopes to the left-hand side of the arrow. We see an isotope on the right-hand side of the arrow. And then you see that blank piece. We're trying to figure out what in the world is this blank piece? What goes where that missing piece is? So remember how we want to approach this. We want to treat that arrow in a similar way to a mathematical equal sign. Well, we know in a mathematical equal sign, what we really have is there has to be an equivalency from the left-hand side and the right-hand side. The total mass on the left-hand side must equal the total mass on the right-hand side. Same thing with the atomic numbers. The total atomic numbers on the left-hand side must equal the total atomic numbers on the right-hand side. So let's kind of look at this. If we look on the left-hand side of the equation, so the left-hand side of our big red line that's splitting this into its two halves, what's our total mass number? Well, our total mass number, we get 9 from the first isotope, highlighted in green, 1 from the next thing. So we're looking at a total mass number of 10. So our mass number is 10 total on the left-hand side. What does that mean? That means on the right-hand side, our total mass number must be 10. These have to be equal. Well, that's going to help us determine what the mass number of that missing piece is. So we have this missing piece. We don't know what it is. What is this missing piece? But what we do know is the missing piece plus the 4 that we already have there with the helium has to equal 10. So we have missing piece. That missing piece plus the 4 from the helium has to equal 10. Well, what will the mass number of that missing piece be? Well, the mass number of that missing piece then would have to be 6. So our mass number is 6 because that's the only way both sides of the equation will have equivalent mass numbers. Now, we want to do a similar thing with the atomic numbers. We want to look at the total atomic numbers on each side. Well, if I look at the left-hand side, I'll be highlighting these in blue. The beryllium gives us 4. The hydrogen gives us 1. So on the left-hand side, our total atomic number is 5. What does that tell us? That means the sum total of all of our atomic numbers on the other side of the equation, the right-hand side of the equation, must also be 5. So now, with the atomic numbers, we're going to do something very similar to what we did with the mass numbers. We have this missing piece, so we have a missing piece, but we know that missing piece plus what we already have. Remember, if I'm looking at the right-hand side, I'm looking at, from that helium, I have 2 for that mass number. The total of the missing piece plus what I already have in place on the right-hand side has to equal 5. Well, what plus 2 equals 5? Well, that tells us that the atomic number has to equal 3. That missing piece must be 3. So now we've figured out what the missing mass number was in green. We figured out what the missing atomic number is in blue. So we're most of the way where we want to go. We just need to figure out fully that missing piece. So I'll kind of show this on the top. What's our final thing that we're looking at? Well, we correctly determined that the mass number of our missing piece was 6. We determined that the atomic number of our missing piece was 3. We just have to figure out what symbol we're dealing with now. So we would use our periodic table, look for the atomic number 3, which element is number 3, which element has 3 protons, and looking at the periodic table, we would see that that would be lithium. So in the upper right-hand corner, I've listed what this missing piece was. So this is how you go ahead and go through this in order to figure out what your missing pieces are. You want to make sure at the end your sum total on the left equals the sum total on the right. And this is something you can easily double check. You know that if those statements are true, the sum totals on the left and the right are equal, you would have had to have done it right. If they're not equal, then you definitely know there's an error somewhere and you want to go back and fix that. So our final answer for this would be mass number 6, atomic number 3, and our element would be lithium for this isotope. One last thing on this slide before we do another example of this is you see a couple different forms of radiation here. I'll use kind of purple to highlight them. The first thing, the 1,1H that I have the arrow pointing to, you can kind of identify what form of radiation it is. Well, that would be a proton. On the right-hand side, we have another form of common radiation that we just got through talking about. Purple arrow pointing to that 42He. Well, we can identify that one as well. That's an alpha particle. So these are some of those things that we just talked about, those common forms of radiation. Now you're seeing them in place in various different reactions and equations. We're going to do another example of this. So here we have another example, and what I strongly encourage you to do is pause the video right now and try to do this problem on your own. So strongly suggest you pause the video, try to do this on your own, see what you come up with, and then check to see what you did was correct and making sure you're kind of following along. So go ahead, pause your video now, try to do this one, and then once you have an answer, continue the video to make sure you're kind of doing it in the right way. So hopefully you did pause the video there. And remember, we're treating this arrow the same way we would a mathematical equal sign. So remember what we're trying to do. We're trying to make the sum total mass numbers equivalent, and we're trying to make the sum total atomic numbers equivalent. So let's start with the mass numbers on the left-hand side. So I'm going to kind of highlight these again. We'll highlight these in green. I have 6 from the lithium, 1 from the neutron here. So my total mass numbers on the left-hand side would be 7. What does that mean for my sum total of mass numbers on the right-hand side? Well, on the right-hand side, that means my sum total of mass numbers must be 7. So remember, I'm trying to figure out what this missing piece is. Well, the sum total of all the pieces on the right-hand side must be 7. So let's look at what that missing piece could be. Well, I get 0 as a piece that's already there. I get 4 as well as a piece that's already there. And now I'm looking for my missing piece. Remember, the sum total of the pieces has to give us 7. So I have a 0, a 4, and a missing piece, and I'm trying to hit 7. Well, that tells us our missing piece must be 3. We're looking at 3 as our mass number of our missing piece. So a similar procedure to what we did with the mass numbers, we're now going to do with the atomic numbers on the left-hand side. Atomic number of 3, atomic number of 0. Well, I have a 3 and a 0. That means 3 and 0 combined is 3. That means on the right-hand side, the sum total of our atomic numbers must be 3. So now I'm looking at what pieces I already have in place to try to figure out what's happening with our missing piece. So for the atomic number, what pieces do I already have? Well, I have a -1 already. I can see that. Highlight that in blue. I have a -1, and I have a 2. So I have -1 plus 2 plus whatever this missing piece is. Remember, this missing piece has some atomic number that I'm trying to figure out. So I have a -1 and a 2, and I'm trying to get up to 3. So that's going to be used to determine what our missing piece is. -1 plus 2 is 1. So in order to get up to 3, that means our missing piece must be 2. The only way we can get up to a total of 3 is if the missing piece is 2. So -1 plus 2 would equal 3. So now in green, we figured out what the mass number of the missing piece is. And in blue, we figured out what the atomic number of that missing piece is. Well, now we'll do it again in the upper right-hand corner. We're just going to put it all together to be able to write out what isotope are we actually involved with here. what is this missing piece? Well, we said that the mass number was 3, so let's get that in. We'll actually do this in red to be consistent with the other one. Our mass number is 3. What's our missing atomic number? Our missing atomic number is 2. So our mass number is 3, our atomic number is 2. Now we have to figure out what symbol we are looking at for this. What will have a mass of 3 and an atomic number of 2? Well, we care about the atomic number because the atomic number is what determines the identity. Which element has an atomic number of 2? It's helium. So our missing piece is what we see in the upper right-hand corner. Mass number 3, atomic number 2. Our element is helium for this. Again, hopefully you tried this, you got the same result. If not, go back and see what you may have done incorrectly and try to fix that in order to make sure you're able to do this. Remember, you can always go back and double check these type of problems. If the mass numbers are all equivalent, then what you figured out for the missing piece has to be correct for that. The atomic numbers total on the left and the right are all equivalent, then what you wrote for that has to be equivalent as well. So again, just like we did on the last one, I just want to kind of point out some of the different types of radiation that you see. You see this 1 ON. Well, what type of radiation is that? Well, that's a neutron. You see on the right-hand side, this O -1E. Well, that's a beta particle. That's a high-energy electron. And you see even a third type here, this 4,2He. What type of particle is that? Well, that's that alpha particle again. So you're seeing these common forms of radiation that we are using. Let's kind of go back and re-show you the highlighting here. You can really kind of just do this the same way to keep all of your pieces straight. Another thing we want to do with nuclear chemistry is talk about the idea of half-life. So half-life is one of those terms that actually the definition kind of sounds like what the word is hinting at. Half-life. Half-life is the amount of time it takes to reach the halfway point. So in our case, half-life is the amount of time it takes for 1/2 of a radioactive sample to decay. How long to get to the halfway mark? Half-lives have very, very long ranges. They can go from very, very short times, much, much less to a second, to very, very long depending upon the isotope. Some half-lives are less than a second for certain isotopes, while others could be billions of years. Each isotope ends up having a kind of specific use, or we figured out ways of using different isotopes that either have short, medium, or long half-lives. So something we're interested in is healthcare and medicine. Some isotopes that are used for medicine have very short half-lives. Their half-lives are in the hour to day time frames, relatively short. Other half-lives that you might be familiar with, other radioisotopes, carbon-14. You may have heard about carbon-14 that's used for radiocarbon dating. Radiocarbon dating is a technique that's used to date things on the historical time scale. You could figure out using carbon-14 dating whether that paper that was written on came from the Middle Ages, 1200, 1100, or if it maybe goes all the way back even farther to 200 or 300. It gives you a dating on a historical time frame. Other isotopes have even longer half-lives. Some isotopes have half-lives in the millions of years. Well, how can you make use of that? Well, if you're trying to date things on a geologic time scale, well, that's millions or billions of years. That would be very useful to use something that has a extremely long half-life to it. So these half-lives can vary quite a bit, from very, very short to very, very long. There's one specific type of half-life problem that we want to do, and I want to show you how to go about doing that problem. So problem reads something like this. A radioactive sample has a half-life of 5 days. If you start with 100 grams, how much will remain after 20 days? Now, here is a type of problem that if you just start doing random things with those three numbers, 5 days, 100 grams, and 20 days, you're going to make an error. You're not going to get the right answer out. If you just kind of panic and just start randomly throwing numbers, it's not going to work. But you can do this problem very easy and very methodically. All you have to do is use the definition of half-life. So I'm going to show you how to do this problem using that definition of half-life. Now you see a two-row table. This is not a dimensional analysis table. I'm not multiplying and dividing. All I'm doing is kind of using that to kind of compare and contrast. So what do you want to start with? Well, how much material did you start with? 100 grams. And now what's really, really important, here's where a mistake happens at. If someone hands you this sample, how much time has passed? Has 5 days already passed? No. No time has passed. You always start your countdown. You always start your clock at time 0. The clock doesn't start ticking until you receive this sample, until you start dealing with that. So you don't want to use 5 days. You want to use time 0. If you're dealing with hours, it'd be 0 hours. Seconds, 0 seconds. Years, 0 years. But you always want to start at 0. Then what you're going to do is you're going to count forward in increments of half-lives. It says the radioactive sample has a half-life of 5 days. So that means I'm going to go forward 5 days. 0 days is our first time point. Always start at 0. Then increase in increments of the half-life. 0 days, next would be 5 days. Okay, that'd be one half-life. Now go 5 days more. That would be 10 days. And here's where a mistake sometimes happens. Sometimes people just randomly double things. You're not going to double things. Our next time point is not going to be at 20 days. We're always counting in those increments of the half-life. So after 10 days, we're not going to go to 20. We're going to go to 15 days. Always the increment of the half-life. If it's 5 days, 5, 10, 15. Our next time point would be 20 days. If we were going farther, we don't actually need to go farther for this problem, but if you needed to go farther, you'd go 25 days, 30 days, 35 days. You're always going forward in the increments of the half-life. Now, in order to solve this problem, you're just using that definition of half-life. You saw where we started. We started at 100 grams in 0 days. Now we look and see what happens at 5 days. Well, 5 days is a half-life. What's the definition of the half-life? Well, half-life means half of it is gone. Well, what's half of 100? Half of 100 is 50 grams. So now we're going to go ahead another half-life. So when we go to 10 days, what's going to happen at 10 days? Well, that's another half-life. We're going to lose half again. So what's half of 50? Half of 50 would be 25. So at 10 days, we'd have 25 grams left. What's our next time point? Our next time point is 15 days. That's another half-life that has expired. So what's going to happen? We're going to lose half of our sample again. That 25 grams, half of 25 is 12.5 grams. Now we're going to move forward another half-life. When we move forward another half-life, so that'd be 20 days. That's where we want to ultimately end at. How much will remain after 20 days? But that's another half-life. That's going to be meaning that we're cutting that amount down in half again. half of 12.5, 6.25 grams. So we're going to see that we end up with 6.2 grams final at the end of this. What I'm showing you on the bottom is just kind of that same thing without the numbers to get you at the idea of every time you have a half-life, you lose half of the material. So here we would be at 0 days, 5 days, 10 days, 15 days, 20 days. You can kind of see when we go from 0 to 5, that's one half-life. The shaded portion represents what you have left. I lost half. Going from 5 to 10, I lose half again. 10 to 15, I'm losing half again. 15 to 20, I'm losing half again. These problems can be very, very straightforward if you just kind of take your time, go slowly, and count through half-lives, and you know what the definition of half-lives are. If you just start randomly doing things with the 3 numbers you're provided, it's probably not going to go so well. A couple of key things you want to remember is you have to start at time 0. You're always starting at time 0. One of the biggest mistakes that gets made is people want to start at one half-life that has already transpired. That's not correct. We want to make sure we're starting at time 0. The other thing that we would want to make sure we're doing so we don't create an error is we're always going in increments of half-lives. So 0, 5, 10. The next one's not going to be 20. It's not doubling. It is going in for our time increments of those half-lives. So 0 days, 5 days, 10 days, 15 days, 20. We're not doubling the time. We're always going in increments of that half-life. If you do those things, you're going to get every single half-life problem correct very, very easily. If you kind of panic and just start randomly getting involved with the numbers, it's not going to go as smoothly. So you can make these problems very, very straightforward just by taking your time and using this definition of half-life. I want to talk just really, really briefly about some of the medical uses of radiation and nuclear chemistry, because that's why we wanted to learn those techniques and talk about half-life and completing nuclear equations and being able to recognize common forms of radiation. It's because these are used all the time in medicine. Now, you could take entire classes on nuclear medicine. That's not our goal. There's entire programs on nuclear medicine. We just want to spend a couple minutes talking about, well, why did we spend time dealing with nuclear chemistry? We spend so much time dealing with nuclear chemistry is there's 2 key uses of nuclear chemistry in medicine. The first is the idea of treatment. You're probably most familiar with this for cancer treatment. You know that radiation can be used as a treatment to try to cure cancer. And the reason being is that cells that are rapidly dividing, that's what cancer is. Cells that have that uncontrollable cell division. They're rapidly dividing. When cells are rapidly dividing, they have to have their DNA exposed. When a cell has its DNA exposed, they're much more susceptible to radiation. That's why radiation can help target cancer cells more so than surrounding tissue. Another thing that goes along with treatment is you may have heard about radiation used for thyroid treatment. Sometimes people with highly overactive thyroids, their thyroids are just working too hard. Well, radiation could potentially be used to destroy some of those extra active thyroid cells such that that thyroid is now functioning more normally instead of overacting, overdoing things. So various treatment paths have been developed that use radiation to treat different medical conditions. The other thing where this can be used as, if you're not treating, trying to cure something, it could be in the diagnostic area. Diagnostic is diagnosing. You're not treating what's wrong, you're trying to figure out what's wrong. And one of the big areas for this is in imaging. What ends up happening for some of this imaging is what you can do is you can use radioactive isotopes or radioisotopes in the body. What ends up happening is you could either ingest or through IV take in some radioisotopes. Those radioisotopes will concentrate in a specific type of tissue. What then ends up happening is that area of the body or your body is scanned. A scanner is then used to detect radiation levels at all the different parts of your body. Where is radiation coming from? Computers then used to take those radiation levels, and you end up producing an image of that area. If you've ever had a MRI that has had contrast agent with it, a lot of MRIs don't use that anymore, but some MRIs have contrast agent. That contrast agent is actually a radioisotope, and that helps provide better imaging of the different interior parts of your body. And each different isotope will congregate in different areas of your body. So if you're trying to image heart tissue, cardiac tissue, you would use a different isotope than if you were trying to image your liver or trying to image, intestines or stomach or connective tissue. Each one would be used for a specific purpose. You may have heard of positron emission tomography, PET for short. That's another one of those examples of using radioisotopes in order to get a diagnosis, an image of what's happening. So this is why we wanted to spend some time talking about some specific things in nuclear chemistry, because it's used in medicine all the time. Not only is it used in medicine all the time, it is a growing field. There are always going to be jobs available for people with degrees in nuclear medicine because it's used so often, and those uses are not shrinking, those uses end up expanding. So this is kind of a highly growing field and very important to our healthcare industry and how we deal and get involved with in medicine, both for treatment and for diagnostic type uses. This is a big sub area in healthcare and medicine.